let's continue. So from last year's class, as we discussed, the transport in the transport layer, there is a transport protocol or some set of rules which basically dictate the communication that goes on, that creates a logical channel between two transport entities. The two transport entities are basically two processes which communicate with each other via TCP, which is the protocol that we will primarily study. It can be some other protocol also. Primarily two are popular, TCP and UDP, but TCP is what we will primarily study because UDP is very, later on we will find is just a very simplified version. These processes can be identified using some transport address, which are typically something called ports in Unix or in TCP. I shouldn't say Unix because this is also used with other operating system in TCP. And the chunks of data that are exchanged during this transport layer communication are called segments. So here this segment, it seems as if the two transport layer entities are themselves directly exchanging segments, but this is not the correct exactly physical interpretation. The physical interpretation, you know, that the segments actually gets transferred to datagrams and to frames and then to physical packets, and then it goes down the network stack, and then again it goes up when it reaches the receiver. So these segments are encapsulated. This also we have studied in this way. Successive headers are connected with the existing payload. What is the current payload? The current payload is the previous layer's entire protocol data unit, okay, or PDU. So the PDU at the transport layer is the segment. It has a segment header and data, but that entire segment is the payload for the network layer PDU when it becomes called the datagram, okay. And you have the packet header and then frame header, etc. So as you go from top to bottom in the network stack, the length of these protocol data units keep on increasing. The transport service must support at least this minimum set of primitives or operations. Okay, there is something called listen, connect, send, receive, and disconnect. Listen is it keeps on listening at a particular port until some other process, other transport layer entity tries to connect. Then some other transport layer entity tries to actively connect with it, with that server or somebody who is listening at a port using a connection request. Okay, there's a special type of a packet. Then there is to and fro data transfer once the connection is established between the both sides. Remember, typically the TCP connection is bidirectional. Okay, just like in a telephone, both the parties can talk with each other. Similarly, once the TCP connection has been set up, there is no distinction between the sender and the receiver. The parts played by both the parties become symmetrical, which means that any of the parties can perform any of the operations. They can send data, they can receive data, and they can request disconnect. But in our examples, to begin with, we will consider that the disconnect request is being done by the client who also requested the initial connection. Oh, okay. So this is not always the case. For example, in a telephone, either of the two parties, once the connection has been established, can hang up the telephone, that is disconnect the call. Similarly in TCP, but we will assume here that the client which started the connection by requesting a new connection, he himself will also request the disconnect. This way of looking at things will simplify matters. So the version of TCP that we will study initially is not the actual detailed TCP. There are the actual TCP. There we will later on find there are certain peculiarities or features which are slightly different, not completely different, but slightly different from the simplified version of transport layer description that we will start to study. Okay, but these differences are so small that once you understand the initial transport layer operation, it will be very easy for you to adapt it to TCP. Okay. Now the transport layer needs to remember the state of the operation, how much information has flowed, what is the current state of the connection, etc. So this is a stateful protocol. Anything that has a state usually can be established with a state transition diagram. In this diagram, the left hand part in dotted line is the server side of the connection, and the right hand side in solid line is the client side of the connection. Okay. So if you study this as such, these two state diagrams are reasonably symmetric for both the parties, except that there is some passive part played by the server and some active part played by the client. In today's class, primarily, we will concentrate on this first connection establishment part. Okay, this part at the top of the diagram. How does this happen? Later on, we will study, after that, we will study the disconnection part, and then we will study the data flow part, which has not been shown in the diagram. So all these three parts separately are, each of them are reasonably complicated. Okay. Each of them are reasonably complicated. Each of them have their own peculiarities, has its own peculiarities. So please pay attention. This is one of the most complicated portion of the course. So you must understand this thoroughly. The connection establishment, sending of data, and the disconnection can be in a simple way visualized as shown in this diagram. Okay. That the client requests a connection establishment to a server which is listening at a particular port. When it accepts that connection request, when it receives that connection request message, it makes a decision about whether to accept it or not. If it can accept it, typically that is the case. It acknowledges that connection request with another message back to the client saying that yes, I allow the connection and I acknowledge this connection. After that, the connection is at an established state, and then the client can send data. It can keep on sending data. Again, notice these special timing diagrams where the time axis points to the vertically bottom. Okay, as I said that this is the type of timing diagram in computer networks that you will have to get used to. Notice that in this diagram, intentionally, to keep things simple, data flow has been shown to be kind of unidirectional. So as if only the client is sending data to the server. This is not the case in practice. Okay. Again, please don't get confused later on when you will also find that the server can also send data back to the client. That is what actually happens. However, here to keep things simple, we are showing a kind of a simplex data transfer model where only one side sends data to the other and the other side only sends back control information like acknowledgements, etc. But that is not the case in practice. Okay. For now, there is no harm. You can consider this simple. Whenever using the send primitive, the client sends data, the server receives the data. And then there is finally when all the data has been sent, or for any reason, the client at any point of time can request a disconnect. Okay. This disconnect is also in the form of a special packet, a special segment, and then the server, if he acknowledges, if he agrees to the disconnect, he disconnects. So this seems quite simple. Okay. However, this diagram completely ignores the fact that these segments that are flowing between the transport and the server, between the client and the server, eventually will flow through the network layer. And this network layer gives no guarantee of when these packets will be, segments will be transmitted to the server side, and whether at all they will be transmitted to the server side. It makes no guarantee about the delay, and it makes no guarantee about whether it will be transferred. Okay, so this is quite bad situation actually. We are saying that TCP will give you guaranteed service in order. Okay, everything, every information, no information will be lost. Information will be transmitted to the application layers at the receiving side in order, perfect order without any loss. And then we are saying that we are depending on a layer at the bottom, the network layer, which makes no such guarantees. Okay, for example, in the post office, say the post office that we use, ordinary letters, okay, just postcards or inland letters or some envelope based letters. I don't think there is any guarantee about the delay or the guarantee that whether at all it will reach the receiver. Means there is no legal guarantee. The post office tries its best, but there is no legal guarantee. Whereas if you register the letter, or if you do a speed post type of a thing, then there is a way to track up to how much this has reached. If it cannot be delivered to the receiver, it will be sent back to the sender. There is a guarantee about the maximum delay that might happen. I think in case of speed post, there is something limit that either it will be delivered within this much of time or it will be sent back to the sender, something like that. Somebody has to sign and receive the letter. So there is a proof that yes, somebody has received the letter at the receiver side. All these things are there. But the situation in computer networks is like similar to our ordinary letters, where there is no guarantee about the delay and there is no guarantee even whether the letter will be transferred or not. So this is quite complicated. Okay, as I mentioned, that it is a marvel that at all the transport layer works and is able to successfully provide the service that it promises to provide, given that it is dependent on a layer which is not dependable. Okay, transport layer in turn, it basically takes the service of another layer which is not dependent. Great. First, connection establishment. So this is a simplified format, but does this work properly? See, the problem is that this does not work properly because there is no reliability. Okay, consider this situation. First of all, can any of you tell me that after sending a connection request, how does a client know that connection has been, means the server has successfully received the connection request? Anybody?
Waits for the ACK to come.
Yeah, so it waits for the acknowledgement, right? So suppose when the acknowledgement is not coming back for a certain amount, as soon as a client for any packet in TCP, okay, later on we will find for any transport layer protocols like TCP, after a client has, both the parties, actually here we will just consider the client, after a packet has been sent, it starts a timer. saying that I expect the acknowledgement for this packet come back within this time. Say I'm just giving an example, say 120 seconds. If it does not get the acknowledgement for that back within 120 seconds, it thinks that the packet, something bad has happened. Maybe the packet has got lost and it resends the same packet. Unfortunately, it does not, the client does not know what has happened to the packet. The packet, maybe either it might have gone lost, but it might also happen that because the network layer routes packets in a peculiar way, it has just got delayed in reaching the server. So within 120 seconds, it has not been able to reach the server, maybe on the other side of the world. Okay. So what happens is it resends another connection request. Okay. So, but eventually the first connection request segment reaches the server, but it reaches the server later in time. That's why these two arrows have intersected. These two arrows would never have
Excuse me, sir.
ordinarily.
Sir, there is some constant noise in the background. Could you mute everyone, sir?
It is not coming from my machine. I am also getting the signal.
Sir, could you mute everyone else?
Kolapuram Mohana some.
Oh, I can mute others.
Yeah.
Students, could you please mute? I think now it is muted, right?
Not really, sir. There's one more student who, he's not yet muted. I guess he's
Okay, I
Kolibara.
am doing mute all. I am doing mute all. So, okay, that will create a problem because if somebody raises a hand or something, it will be okay. Let me mute all and then we'll continue. If you have questions, keep it for the end of the class. I will come back and discuss. Okay, so in normal situation, these two would never have intersected. These two arrows would never have intersected. Okay, but here in this situation, they do intersect. Why? Because the first segment has got delayed and has reached the server later than the second segment. Although the second segment started from the client later, it has reached the server first. This can happen. Okay, this can happen. This is not a made up scenario. This can actually happen. So it is a big problem because now the server thinks that the client is requesting another connection. Okay, how does the server know, poor server know that this is actually the request corresponding to only one connection, but because it is receiving two different packets. But I think I need to ask a question also. Can you okay, so now I have a question. Can you, before I go to the solution, can any of you tell me what is the solution to this problem? How will the server know that?
Sir, if the packets could have a expiry, maybe something.
Okay, so one solution is if the packet has an expiry. Okay, then any other solution?
The two connection request might have a gap, like if the gap is between that time limit, then it will consider it as one request.
Okay, But
It can maintain
okay.
the state.
Yeah.
The server can maintain the state about a client that it already has sent the acknowledgement for its connection, so it will not accept any other new connection until the disconnection request has come.
Well, yes, until the disconnection request for whom has come.
I mean, if during their conversation between the client and the server, suppose one of the parties send the disconnection request and the disconnection is successful, only after then the server will accept another
Yeah,
connection
that is fine.
request
That
from.
is fine. So basically, you are now saying that the server will not receive connection request, the delayed connection request one, and because it has not received a disconnect request from the client for connection request 2,
Yes, sir.
right? Because
Yes, sir.
connection request 2 is the current connection, right?
Yes, sir.
Which means that now you need to pair up connection and acknowledgements using some, which means every connection request now should have an identifier. Or in other words, every segment that starts a connection should now have an identifier which uniquely identifies that connection, then pairs up its acknowledgement with that segment. Okay. And the other solution that was first suggested is kill off old packets like the connection request 1 segment, which is taking too much time to reach the other side of the server, kill it off. This is also one solution. Now we will discuss, these are the two fundamental ways. You have already answered. These are the two fundamental ways of solving this problem. One is to kill off old segments, and the second is to somehow identify what segment corresponds to what state of the connection by giving some identifiers to every segment, so that you do not get fooled about any new segments coming in, whether this is a new connection request or this is an old connection request which is delayed. Now we will discuss these two solutions in detail. Okay, both are used in practice and both of them we will discuss. Okay, so this is the fundamental problem. How will the server differentiate whether connection request 1 is a new connection request or a duplicate of connection request 2? This is called the delayed duplicate problem. Okay, there is a duplicate in the network for the same connection, but it is a delayed. Okay, this can also happen now when it can also happen if the server suddenly disconnects and then the client reinitiates the connection with the same port. So distinguishing between these two is also essential. Okay. Now, several solutions. This is an old problem, okay, as old as computer networks itself. So several people, very, very clever, intelligent people have worked on this. We are not the first people to consider this, okay. So many people have worked on this and they have proposed different solutions. One thing is whether the solution proposed is correct and or whether the solution that is being proposed is performance is acceptable. This is a very, very important trade-off. In computer networks, you will find that often we accept protocols which are not fully correct. Means through simple analysis, it can be shown that the protocol is not correct. It will not always succeed. There are corner cases for which the protocol will fail. But for 99.9999% of times, the protocol is works and it gives you very good acceptable performance in practice. This is an important concept because computer networks, the user experience is an important feature. Okay. An user who is connected to a network expects some amount of quick turnaround time for his data and all the web pages he is trying to access, or his entire experience when he's trying to transfer a file, whatever. Okay, when he's trying to get a page by HTTP, whatever, there is an expectation on behalf of the user. So these have to be balanced. So we want for the delayed duplicate problem to have a solution which is either correct by construction, the protocol, or at least it is acceptable. It is not always correct 100% of the times, but it is correct a large, very large majority of times. Means very large means over 99% maybe of times. And the performance is very, very good for handling this delayed duplicates. Now we will consider one after the other the different solutions that have been proposed. Okay. First, we will consider some solutions which are not really practical. Means people have thought about them, then they have rejected them. Okay. The first one was they say that see, I require an identifier. Okay. For any connection. So your transport layer identifier is the port for the processes. Why don't we change the port number for every new connection? Even for a delayed connection that you initiate, you change the port number. So once don't use a port number if it has been used already. Okay. So then delayed duplicate packets will never find their way to a transport process. Okay. There will be no confusion. Okay. So, I mean, this is a big problem. This is feasible solution. The problem is that now server processes will start offering standard services. That offer standard services will keep listening to arbitrary ports. Okay, and it will make it extremely difficult for processes trying to connect. Do you understand what is the solution? The solution is that say the server process will now use ports just for the second, just because it is another connection request. This will now use a different port corresponding to that server process, because in the meantime the server process port has changed. First of all, how will the client know what is the port that the new port that the server process is using? How will he know? It's quite difficult to know, right? But if this could have been implemented, then there would be no problem, because say the delayed connection request one comes to the server with some particular trying to connect to some particular server process. The server will say that, well, no, this is an old port that I was maybe using 3 minutes earlier. So this must be the delayed duplicate. This I am not using currently, so I'll reject this. So there is no possibility that the connection request one segment will be accepted at the server. So no problem. But then this is a huge pain that there is no concept of standard ports actually. Okay, it's very, very difficult. So it is not feasible. Second, I will give each connection. This second one actually looks reasonable, but there is a problem. See, we want identifiers for every connection. Okay, this is what I said. One of the fundamental techniques is you assign an identifier chosen by the initiating party, the party which starts the connection, and you put in each segment. Fine. In that case, what happens? Well, if connection request 2, which so both connection request 1 and connection request 2 both will have the same identifier. Okay, because connection request 1 has not been acknowledged back to client. Client says, okay, I have not been able to successfully establish the connection. Let me initiate connection request 2 with the same identifier. The server accepts connection, reaches connection request 2 first, and it starts the connection. Accepts server acknowledges maybe connection request 2 and it starts the connection. But in the meantime, the delayed duplicate connection request 1 comes with the same identifier. Now, the logic is the server will now not accept connection request 1 because it says that with the same identifier. What is the identifier? I don't know. Maybe a number. Some connection request has already been accepted on my side with a unique identification number. So there cannot be another connection request with the same identification number. So I will reject it. How does the server know? Well, the server in the time between this arrow connection request 2 arrow and the time at which this connection request 1 arrow reaches it, in this small interval of time, it is remembering the history of this connection request 2 identifier. The problem is, what if the server, and remember that the server is not only handling one client possibly, it is handling millions of clients. So for every client, it is remembering this type of a connection request identifier history in the form of these tuples. Okay, peer transport entity, that is the sender, client, and connection identifier. These tuples it is maintaining. What is the peer transport entity? Well, probably the IP address of the sender and the connection identifier tuples are being maintained. But this history might be lost in case the server crashes in the time between it received the first connection request 2 and this time. In between, if this server crashes, then that history might be lost, because a server crash might also be a situation where either all the memory content corresponding to the server process is lost, because a process crashing means the operating system typically will release all the memory that the process was holding. Its entire footprint will be released, and again the process will reinitiate. But in the meantime, it's, remember, memory is volatile. Okay, this is a fundamental advantage and a fundamental disadvantage. Main memory in a computer, in most computers, main memory is volatile. What is the advantage? Advantage is because it is volatile, it is relatively fast. Electronic technology is such that volatile memory typically is faster than non-volatile memory. Okay, in general. The disadvantage is this type of things, that data might be lost. Okay, for something which you suddenly, and there might also be hardware crashes, like say suddenly the power is lost on the server. That can happen. The entire server loses power, then it reboots, the operating system reboots. But if the operating system reboots, then in the meantime, of course, the process that was there, everything has been wiped clean from memory. And operating system will also, if it's a daemon process, finally it will start it. But in the meantime, its entire history is gone. So this type of problems will happen. This history cannot be stored indefinitely. No server will give you a guarantee that so much of history indefinitely will be stored. And it's not practical. So how much history will you store? Not practical. Third is what one student suggested. Okay, that you devise a mechanism to kill off edged packets that are still hobbling about in the network. That is, you restrict the packet lifetime. What is the meaning of this? Well, connection request 2 reached the server fine in reasonable amount of time, but the connection request 1 took lot of time to reach the server. what if there was a magical entity in between the client and the server, which looks around, which roams in this space between the client and the server, looks at all very old packets going from the client to the server, and the packets which look suspiciously old, like very, very old packets. In network terminology, say 120 second is the threshold, but there is a packet which is above 120 second, 150 second is a very old packet. It kills off that packet so that these packets no longer will reach the server. Why it kills off the packet? Because it knows that the client also knows about this threshold of 120 seconds. And since already when the packet starts, since when the packet was fasted, of course, the packet needs to have a timestamp that it started at this time. Otherwise, how will that entity know, magical entity know that this packet started at this time? So the packet started at some time t. At t plus 120 seconds, the client still did not get any acknowledgement, anything. OK. So basically the client was expecting that within 60 seconds it will be delivered to the server. So it gave twice the time. OK, so 120 seconds, 60 seconds for this side and 60 seconds back to itself. Total 120 seconds were given. Within 120 seconds, it did not receive any acknowledgement. It resent the second connection request. So the super entity understands that, well, a duplicate for this packet must have been sent by the client already. So there is no harm if I kill off this packet, because whatever service this was supposed to provide has already been being provided, or it has been initiated by the sending party. So it kills off the packet. But now there are so many problems. OK. How will you restrict packet lifetime? First of all, one, you can do a restricted network design. OK, you can prevent packets from looping, binding the maximum delay during network congestion. Network congestions can happen when suddenly the delivery time increases. But this is very, very difficult to implement in the network, particularly in the internet, particularly in the way the network layer works. OK, it's quite difficult in terms of time that you will guarantee the delivery time to be bounded by this, and you will kill off that packet, because that's not how the network layer works. Some packets can take more time. It is expected to reach within 60 seconds, and it is expected you will get back your answer within another 60 seconds, but nothing is guaranteed. So if we impose the first restriction, that is violating the fundamental property of the network layer, which does not give any such guarantee. So this cannot be done. Second is, as I said, so you have to timestamp each packet. OK, you define the lifetime of the packet in the network. The packet is, say, this started at this time plus 60 seconds plus 120 seconds have passed. So definitely its duplicate has been sent by now. So I will kill it. OK. But what does this mean? These super entities typically are the routers. I mean, these godlike entities which can kill a packet. These packets, if you look at the whole diagram, OK, at the beginning of this chapter, it goes through so many routers. OK, these segments get transformed to datagram packets, and it flows through several routers on the way to the final destination. These routers can kill off the packets. They have the power to kill off the packets. Nobody else can kill off the packet, because there is nothing in between, only a set of routers. Now, question is, this is a long way from the sender to the receiver, distributed over a large geographical area, maybe over so many time zones. OK, so now a router, say R3, needs to take a decision. Will I kill off this packet? So then it will need to know that, look at the timestamp and decide, okay, this is the timestamp, but this started at 10 a.m. But in which time zone 10 a.m.? Because on my side, I'm still not 10 a.m. I'm at 8 a.m. So what the hell is happening? I mean, this looks to be forward in time to me. This can happen because the sender is in a forward time zone. Which means now time zone information has to be added to the timestamps. Okay, and all the routers have to take through these calculations. Okay, this was the time zone at which 10 a.m. it started now, which means that time with respect to my clock, local time, etc. All these calculations. So much of problematic things cannot be imposed on the router. Router has to take its decisions very fast, as we will see when we study the network layer. So that is a huge problem, this time synchronization across routers, where every router has knowledge about every other router over which this packet has probably come, and including the starting point. This is a big problem. Again, this cannot be accepted, although in principle this seems okay. In practice, its implementation is difficult. That's why this doesn't work. The third one is, say, okay, forget about packet. Okay, you put a hop count on each packet, put a number, maximum number, say 10. When the packet starts, what does 10 mean? 10 means that when it reaches the next router, and the next router would forward it to some other router. Okay, again, let us look at this diagram to understand. So on this, it reaches router R2 as the first router. This is called like the first hop router. Okay. When it reaches this router R2, now we will, my concept of time between the sender and the receiver entity is gone. Now my concept of time is discretized in terms of number of routers it has passed through, which is not perfect, because how many routers it has passed through does not always give me an idea of how much time it has spent in the network. Well, it is possible that it has passed through 10 routers and it has spent less time, that it has just passed through 2-3 routers. It is possible, because again, routing also is a funny business. Okay, but to keep things simple and to employ simple integer arithmetic, to keep the operations very simple, we devise a scheme like this. When the packet starts from host H1, we say that, say I impose a hop count 10. What does 10 mean? 10 means that the maximum number of routers that this segment is allowed, or this packet datagram, when it becomes a datagram in the network layer, that it is allowed to hop over before it reaches host H2 is 10. The first router R2 that receives this datagram immediately, just blindly, okay, by force, decreases the hop count by 1. Okay. Then it does some calculation and decides that the best route for this packet to go is to router R4. It could have also sent it to router R1, but it did not. It decided based on its calculations that R4 is the way to go. How does this do these calculations? We will study when we study the network layer. It's very interesting. Anyways, now when R4 reaches it, that number it has received has been already been decreased from 10 to 9. So it has 9 more routers to go over. Maximum it is allowed to go over 9 more routers. Immediately R4 decreases the count to 8. Then it does all other calculations of which way to send the packet. And again, R4 decides the way to send this is to R3. When R3 receives the segment, immediately it decreases the count to 7. And it sends it to, finally decides that it can be sent to host H2. Now at every moment it compares the value, maximum allowed value, that field is preserved and the current hop count is also preserved. Okay, in the it becomes part of the packet. So it compares the current value with the maximum allowed value in the packets. So why did this packet route successfully till host H2? Because its count never came to 0. If at any point of time, say unfortunately or because of any reason, the hop count has been set to 3, means it can max flow over 3 routers, then it will be little problematic. Okay, so like I think what will happen is first it will decrease to 2, then to 1, and then router R4 will not bother that it has become very small. When router R3 it reaches, it becomes 0, R3 will eliminate the packet. Okay, or if this R3 is just the gateway router to the host, that is the last router before the host, then it might allow it to go to the host. But if it is not the last router to the host, in that case, it says that, well, your time is up. It kills it off, means it does not forward it anymore to any other router. Okay, so this way, based on a router count, this thing hop count, these packets can be killed or not. Okay, so it initialized to a maximum value and it keeps on decrementing each time the packet traverses a single hop. Okay.
Sir.
Now the design challenge with this is one additional problem is, so this is widely implemented. This last thing, it is not perfect, as I said, because it kind of ignores the concept of time, but the concept of time still is there because there is an acknowledgement issue also. Acknowledgements have also to be did. Till now, we were considering situations where we said nothing about the acknowledgement, but acknowledgements can also normal segments. They can also be delayed. They can also be lost on the way. So this has to be solved. Now, very important work in this domain was about selecting the sequence numbers, particularly the initial sequence numbers. This was done by a gentleman called Tomlinson. In 1975, he published a paper in an ACM journal, I think, about the selection of sequence numbers. So this is a surprisingly complicated topic. I mean, if you first look at it, you would not realize that it can be so complicated. Okay, I mean, what's the big deal? I mean, selecting initial sequence number for any, so every segment will be now identified by a sequence number. And how will you will keep on incrementing the sequence numbers as you send the next segment, etc. Okay. But the sequence numbers must be such that they should satisfy two important requirements. They must be chosen such that a particular sequence number never refers to more than 1 byte. Okay, for byte sequence numbers at any one time. So consider simple situations where every byte is it's just like every byte is a different sequence number, which is fine. I mean that's fine, not a problem. So no 2 bytes will have similar sequence number at any given point of time. So how to choose the initial sequence number in this case becomes a big headache. Okay, as we will see. And the valid range of sequence numbers must be positively synchronized between the sender and receiver whenever a connection is used. Positively synchronized means that both the sender and the receiver will help each other in recognizing segments which are inside, which have a valid sequence number or we do not have a valid sequence number. Now both sides will impose sequence numbers. Okay, we will start our discussion with as I said, with a situation where we will show only one side sequence number. But as we go on to TCP later on, we are not yet started the actual study of TCP. Please remember, we are now describing in general context transport layer. Okay, but when we move to actual TCP, we will discuss the sequence number, both side sequence number, how they help each other. Why the initial sequence number selection is important? The first subtopic, so to say. Well, the initial sequence number is important if you look at this plot. Suppose it has been estimated that the packet lifetime in a network can be maximum T. That within this T time, either it will be killed off by some router because its hop count would decrease to 0, or it would have reached the destination. Either of these two will happen. That is guaranteed. Okay. Again, that is not guaranteed, but that is more or less certain. It has been estimated. TCP continuously estimates a parameter called round trip time. How much time is expected for a packet to come back or an acknowledgement to come back to itself. Round trip time, what is the round trip time from sender to receiver? Continuously it keeps on updating, estimating and updating this using particular formula which we will study later on. So it has been estimated that the packet lifetime is maximum T. Suppose connection 1 between some client and the server starts. So the sequence number is plotted along the y-axis, time is along the x-axis. Notice how the sequence number increases. Suppose the initial sequence number is 0. So this black straight line is a straight line starting from the origin. It is increasing linearly over time because sequentially it is every byte is increasing the sequence number by 1. At some point of time, the connection crashes. Okay. Now notice this blue parallelogram that is shown. What does this blue parallelogram means? Well, it means the entire time and sequence number zone, which is a region, which is a kind of a danger zone. In this zone, there are the packets which started with that sequence number. They are probably still in the network. For example, if you just consider this horizontal point, it is still in the network till the end of this blue line in the parallel. Consider any starting sequence number, say this is 10. Till this point in the network, time T, it is there in the network. Okay, in this way, it is, this danger zone is very important. Now, when connection 2 has crashed, connection 2 finally again initializes, but it initializes unfortunately somewhere in the danger zone. With respect to time, it initializes at this time because it is ready. But the mistake it made is it initialized it at a value where this danger zone is, it is within this danger zone. So it becomes, when it starts connection 2, it becomes very, very difficult to differentiate between packets, new packets from connection 2 and old packets which are possibly still in the network, because there is so much of blue area on the right side of this vertical straight line when connection 2 started. And this parallelogram for connection 2 and this blue parallelogram for connection 1, they are overlapping. So in the overlap zone, you are getting packets which have same sequence numbers possibly because its selection of initial sequence number was wrong. So what can be done to solve this? Either you choose your initial sequence number to be extremely high It is so high that connection 1 would not have reached this sequence number at the time it crashed. Okay, so no issue. You select such a high sequence number and you start your second connection from such a high point that no way these two parallelograms can intersect. And in that case, there is no problem. Or you wait. Okay, you not wait, you start it at a time, but you start it at a very low point. What does this low point start means? Low point start means that within this time, the old packets have probably all reached the destinations. Okay, because again, there is no overlap between the blue parallelogram and the orange parallelogram. These two are the solutions. But now this means that you need to remember what is the time at which this crash happened, what is the danger area of this blue parallelogram, and accordingly you need to select your orange parallelogram starting points. So these are complicated issues which we will keep on continuing to study in the next class, which will be next Monday. So happy Republic Day to you in advance and best of luck for your class test on Sunday. Thank you. I'm now stopping the meeting recording.
Sir?
Yes.
Sir, in the solution that where we were killing the packet
Yes.
by hop count. So in that case, suppose the client and the server are very large distance apart, then means there is no way to actually connect the client and the server with less than that many hop counts. So how will they connect then? It will always kill those packets, right?
No. So the hop count is not 10. It will be set to a higher value.
Okay.
Accordingly, it will send. Well, it will be a defensive choice. Okay, it will give it sufficient room. That say, well, most of the times the packets will be delivered within 15 hops. So in that case, it will probably set it to 25 or something. I'm just giving an example of 30 or something like that. So that it is okay because see this also depends on the time. Okay, so the senders might or the receivers might also continuously the senders might also continuously experience delays in sending packets, etc. if the hop count is small. So in that case, it understands that currently the network is facing congestion and it is going through lots of hops. So it might, depending on that observation, it might increase the hop count also, saying that, OK, I will just allow it to go over a few more routers. When the router straight route faces, I mean, the shortest route, in a sense, it faces congestion, the routers might decide to send it over a longer route, but which means that the hop counts will be larger hop count is required because it will pass through more routers. OK. So as I said that the packet routing is funny business. A packet from India to USA might go first to Europe, then back to Russia, then to Japan, then to China, then maybe to Philippines, then to Australia, then to South Africa, then to Brazil, then to Mexico, then maybe to USA, something like that, which doesn't make much sense geographically, but it might happen in networks. Okay. Okay. Thank you. We will discuss all this later on. Yeah, as I said, it is on Saturday, right? Oh, no, not Sunday. Sorry, very sorry. It is on Saturday. Sorry, 30th January is Saturday. Test is on Saturday. Somebody has said. I'm very sorry. So I have sent a mail. I have made the same post on Moodle. It is on Saturday. Thank you. Please do not send me any answer by email. Those will not be considered. You have to submit it in the Moodle.